Dr. Jan Feld is a senior lecturer in economics at the Victoria University in Wellington. He's published a number of articles on a wide range of topics in economics, psychology, and linguistics. I'm particularly interested in his talk because he's trying to figure out for us what scientific studies we should actually believe, which is at the heart of the kind of stuff we're concerned about as skeptics and promoting science. So over to you, Jan.
Right, okay. I was still waiting for my presentation to load, but it's good to be here. Not sure if the sound is working.
We're just getting your presentation up.
Great. It still says client has disconnected on my end.
Mm-hmm.
Okay, great. I can see my my slide now. I see the clicker. Perfect. Everything looks great. So okay, perfect. I'm glad that finally worked out. It's good to be here. It's good to speak for an audience full of lovers of science. I'm a scientist myself, and it's very easy to love science if scientific studies tell us what we kind of anyways believe to be true. But what do we do if the rubber hits the road and a scientific study tells us something that we didn't think was true? So if I read the room correctly, and if skeptics haven't changed their agenda, I believe that many of you still are skeptical of homeopathy as medicine. Now, imagine that a study finds positive effects of homeopathy on health. Right? So as a good skeptic, what do? Right? Do you trust the science, or do you kind of stand your ground and kind of maintain that homeopathy is nonsense? So would you trust the science? Well, I wouldn't, right? So there are a lot of bad studies out there. So I've been doing research, empirical research for around 10 years, and kind of I've now seen how the sausage is made. And you're probably aware or can easily imagine that studies showing that homeopathy works can be of bad quality. So the case I'm trying to make is that even serious studies published in top journals are often wrong. And so my background is as a social scientist. So I'm kind of most familiar with studies in economics and psychology. And kind of when I say science, kind of my experience is mostly from the social sciences. But I think you'll see that many of the problems I describe apply to other sciences as well, like medicine, for example. Cool. So how good is serious science as establishing empirical facts? Right? So there's some things we believe to know about the world, right? That we have learned from recent studies, right? For example, that intelligence declines with birth order, right? So firstborns are smarter than secondborns, then thirdborns, and so on, right? Or that teachers, more experienced teachers are better teachers, right? Or if you take kind of branching out from the social sciences, if you take this drug like aspirin, it reduces your headache. Right? So how good is science at giving us those truths? Well, we can find out with replication studies. So in replications, researchers redo the study and see if they find the same results, right? So the idea is that you follow the same research protocol, use similar participants, and usually also larger samples. And a successful replication shows the same results as the original study. Right? So kind of that's the kind of science that we're hoping for, right? If something is published in an academic journal, you can redo the study, you would find the same results, it's robust, and it's there, it's the truth. However, you might also have a failed replication, right? Meaning that the replication does not show you the same results as the original study. And so that could mean that there was a mistake in the replication, or there was you didn't find anything by chance. That is unlikely. What's more likely is that the original study is wrong, or that their small changes in the context led to a different result. Right? So we can never repeat the same experiment twice. Right? So even if you use the same participants, they will now have had experience with the experiment in the first place. Time will have changed. There might be a different season now, right? So it's impossible to run the same experiment twice. And authors of original studies that fail to replicate might say, well, that's because your replication is different. You made some slight changes in the context that matter. So what I'm arguing is that it doesn't really matter. Both are a problem, right? So either the original study was wrong, or the original study was not robust enough so that small changes in the context made it fall apart. So how many studies now fail to replicate? So, and the short answer is we don't know. So most studies don't get replicated. And just recently, there have been some concerted efforts to try to find out how robust science is. And so I'm going to talk about the replication attempts in the social sciences. And so the most popular replication attempt has been done in psychology. So a team of researchers, a really large team of researchers, have done a fantastic job of trying to replicate 100 studies published in top psychology journals. And they failed in 64 of them. Right? So 64% out of articles published in top psychology journals could not be replicated. So it's a big fucking deal. In economics, things are a little bit better, but still not what we were hoping. So out of 18 studies published in the top journals in economics, 6 failed to replicate. And out of social science studies published in Science and Nurture, so those are two, Science and Nature, those are 2 of the most prestigious general interest journals. 8 out of 21 studies failed to replicate. So you can see that we have a problem. How can we trust science if between 33% and 64% of studies published in top academic journals don't replicate? And so the short answer is, well, we can't, all right, or we have to be more skeptical. And so that's why I am more skeptical of scientific studies than the average person. And that is, of course, except for studies referred to as Skepticon, you should believe those without a doubt. But any other social science studies in particular, just have that in the back of your mind that many of them don't replicate, and you don't know if the study that you're looking at has been or would replicate or not. And so a broader point is, if our studies in the top journals don't replicate, how can we ask others like flat earthers and vaccine skeptics to trust the science? So of course, if we get into the weeds, we can argue that some studies are better than others, and that's exactly what I'm going to be doing in this talk. But I think we'll have a much stronger case if the science that we produce in general would be more reliable. It'd be much easier to refer to science as an authority and of something that should generally be trusted. Now, so in this talk, I look at 3 things that can go wrong with science and then provide one solution. So the first big bucket of things that can go wrong with science. Let's see if that clicker works. Yes, there we go. Okay, so the first big bucket are bad scientific practices. So I'll keep this short because you're probably familiar with those. So one of them is fraud, which is probably rare, which I haven't added here, but it's also a problem, is just mistakes. So my papers often have thousands of lines of code, and so there might be a coding mistake in there. No foul intended, but yeah, so there might be just mistakes that lead to wrong results. Then there are poor study designs. So imagine a study that does not have a control group, it's not randomized, or researchers confusing correlation and causation. So my sense is, so that's happening, of course, but my sense is that researchers pay a lot of attention to those issues, and we learn as a discipline. So the methods we used 10 years ago in economics are not the same methods that we're using these days. And then there's poor statistical analyses. So the famous term p-hacking is as a researcher, you try different analysis to try to find significant results. So we like significant results. They're more flashy, they're more likely to get published. And as researchers, we have to make many decisions, and it's all too easy to kind of be guided by how they affect our significance levels as well. Now, and another problem is selective reporting. So we might have 10 different outcomes that we're looking at, and then all kind of measure the same thing, and only one of them comes up statistically significant. And we'll pretend that kind of that's our main outcome of interest, and we ignore the other ones, or put them somewhere in the appendix. The second problem is less intuitive, but nevertheless important, and I'll call it lack of statistical power. So if we hear of an effect or correlation or some finding in literature, that probably comes with a statistical significance. So it's not a definite finding. Any findings with data are probabilistic, and statistically significant does not mean true. All right, so a statistically significant estimate can be either true or a false positive. And so things are looking bad if there are few true and significant estimates and many false positives. So kind of let's dwell on that for a second. Right? So we have true and significant effects are less likely, right? Which is bad. There's a small prior probability of the effect being true. So just as an extreme case, imagine that you're investigating a research question which is impossible to be true because it defies the laws of physics, right? It just cannot possibly be true. Then even if you find a significant estimate claiming that it is true, you kind of know that's a false positive. And so with a small prior probability of the effect being true, the true and significant effects become less likely. Points 2 and 3 are having a small sample and the effect that you're trying to detect being small. And so those two combine to what we call low statistical power. And so low statistical power means there's a low chance of finding a significant effect if the hypothesis is indeed true. And on the other hand, we have more false positives, or false positives are more likely if there's a small prior probability of the effect being true. So let's see those kind of with a numerical example, or two numerical examples. So the question we're facing is, we're seeing an estimate that's statistically significant, either because we did the research or because kind of we see it somewhere in the news. And so what I want to know is, given that there's statistically significant estimate, what's the probability of the effect actually being true? Now, I'll contrast two cases, and kind of I want you to imagine that everything else about those two cases is the same, right? And so the good case has a 50% prior probability of the effect being true. So it's a question, it's very, in effect, it's very plausible. It's a toss-up whether it's true or not. And you have a large sample that gives you 80% statistical power. And your cutoff level, kind of where you decide whether an effect is significant or not, is 5%, which is the standard in many literatures. And so then the bad case, so it's a bad case, but it's not a case that is kind of unheard of, is that you investigate an effect that has a 10% prior probability of being true, and your statistical power is 30%, right? Okay, so for those two cases, what's the chance of a significant estimate being true? Well, in the good case, that is 94.1%. So finding a significant estimate means, well, the effect is probably true. In the bad case, it is only 40%, right? And that is only driven by the difference in prior probability and low statistical power. So what I make of this, and kind of guidelines that you might want to take away, is that if you see improbable effects, and if any plausible effect would be small, right, and there are small sample size, then my conclusion is that it's probably a false positive. And so the homeopathy study kind of alluded to in the beginning, if that has a small sample size, the effect is improbable to begin with, I would expect. And any effect, of course, would be small, because otherwise we would have already discovered the great big benefits of homeopathy. So even if there's no other monkey business going on with the study, I would think it's probably a false positive. So the third point is missing estimates. So of course, not all possible estimates end up in the scientific literature. We have publication bias, so only some studies get published, and some studies don't even get written up. So let me illustrate this point kind of with an example. So it's hypothetical, right, but something related to my research. let's say we want to estimate the effect of role models on test scores. So the idea is that having a teacher that has your gender or your ethnicity will kind of be beneficial to kind of students, because you can imagine they can use examples that students can relate to. Students kind of aspire to be like their teacher. That might be more likely if the teacher looks like you. And so we have 4 researchers, and these researchers all investigate this research question, and they don't talk to each other, right? And they come up with these results. So first researcher finds positive and significant results. Second researcher, positive and not significant results. Third researcher, negative and not significant results. And the last researcher, negative and significant results. So we can see overall, it's not a compelling story for positive role model effects, right? What's interesting is what would happen next, right? But it's an example, but it's plausible that the positive and significant finding gets published, gets cited, gets featured in the news. The positive and not significant finding gets written up but not published. And then the negative and non-significant result doesn't get written up, maybe gets presented at a conference, and the negative and significant result doesn't get written up. So this first study, that's the one you hear about in the news. It gets published, cited, it has an intuitive result. The first 2 studies, well, that's the ones that we researchers are aware of, right? So we're aware of studies that are written up, maybe published in working papers, right? But still, they tell a compelling story that they're probably role model effects. Now, if we add p-hacking to this problem, right? The researcher who found positive but not quite significant results, meddled with the analysis, tried it a few different things, and then found significant effects, then they would get published. And now there seems to be a consensus in the literature. So where does this leave us? What do we do now? So if we're lucky, the research question that we're interested in has been addressed by many studies. And you might be thinking, okay, meta-analysis might be the solution. So meta-analysis combine multiple estimates, in essence, by taking an average. It's a bit more complicated, but that's how you can think of it. And so will averaging all existing estimates give us one credible estimate? So here you might say, well, we should not trust an individual study, but we should trust what the literature kind of comes up with, and the literature kind of gets distilled by meta-analysis. Each study is a piece of the puzzle. All studies together kind of show us what's really going on. The problem is, if there are bad and missing studies, averaging overall studies is not going to be enough. All right, so that's your classical garbage in, garbage out problem. Now, there are ways to correct for publication bias. I'll just name one of them, and that's the trim and fill method as an example. So here we have the kind of a graph that's showing the sample size and the estimates, and kind of from the pattern of these estimates, we can see that there appear to be some missing estimates, right? Those might be the studies that have not been written up because they didn't find results that they thought they could publish. Well, then the trim and fill method imputes these estimates. So imputing is a fancy word for kind of making them up with some statistical methods. And then you would just take the average over all the existing and the imputing, the actual and the imputed estimates, and those ideally give you a good picture of what's going on. Now, of course, we don't know how good these bias correction methods are in practice. So researchers that propose them are very smart, and they show with math and simulations that they work, but we don't know kind of, well, how good they are in practice. We need a benchmark. Good news is that there is one benchmark out there, which are pre-registered multi-lab replications. So psychologists do a fantastic job of, sometimes when there's contentious research question, where there are kind of 2 sides and people kind of don't agree whether an effect is real or goes in one direction or another, they agree to kind of once and for all answer this question by telling beforehand which how they're going to answer the question, so which experiment to run, and then run it simultaneously or close after each other in multiple labs, usually in different countries. And you can see that the pre-registered part leads to less scope for p-hacking, right? And also kind of they agree to analyze all the data in the same way. And the multi-lab part means that we have a large sample size, or there's a large sample size. Now, so kind of with this benchmark in mind, we can see how these multi-lab replications compare to meta-analyses. And for 15 research questions, they're actually meta-analyses and multi-lab replication, addressing exactly the same question. So we can see, do they show the same result? And they often don't. Right? So for 8 out of 15 research questions, replication studies found different results. Right? So again, this is a big deal. We often take meta-analysis kind of to show us the consensus of the literature, and kind of for more than half of them, the replication studies show different results. And 7 replication studies found no significant effects, whereas the original meta-analysis found some. And 1 replication study even found significant effect in the opposite direction. And popular bias correction methods did not improve the results. So this is bad news. Okay, so where are we at? Studies often fail to replicate. Meta-analysis are often wrong as well. Right? So how can we find studies that we can trust? Well, we can conduct super studies. So don't Google the term, it's not out there yet. We made it up, but I'll hope to convince you that the name is justified. So super studies answer the same research question using the same methodology with data from different contexts, right? Like different countries. And so multi-lab replications are one type of super study. So what's the advantages of super studies? Well, they have a larger sample, meaning more statistical power, can detect smaller effects. And they use the same methodology, which leads to comparable estimates. Right? So often, even in meta-analysis, estimates are done quite differently. Imagine a study in medicine. Some test the medicine, a drug against the placebo, others against some other drugs, right? And so it's really difficult to compare all these results. And in a super study, you can kind of standardize your approach. So let's kind of go back to our question on role model effects. Right? So in the ideal world, which I'm envisioning, is that all these 4 researchers, instead of all doing separate business, join their efforts and kind of write a paper showing all the results. That means there's no missing estimates, there's a lot of statistical power, and they have the ability to compare estimates in different settings, and they can tell us really what's going on. So there are examples out there of super studies. I mean, most studies are not super studies, but just some examples are the Pfizer vaccine efficacy study. It's outside of my field, but I kind of had a brief look at how it's done, and it's a fantastic super study. The same methodology applied to different contexts, and it shows convincingly that it works. Another question is, there's a super study on the effect of birth order and personality, right? Raising the question of whether second-borns or third-borns have a different personality compared to their first-born siblings. And for more than 100 years, psychologists have found birth order effects on personality. And then in 2015, a super study came along and found, he analyzed the question with 3 large data sets and found there's no effect. And this result has been confirmed. And the study that I've been involved in, we've looked at the effect of sibling sex on personality, whether you grow up with a brother or sister, and used 12 different data sets, and it has no effect. Okay, so what do we do now? So we need to do more super studies. So they will require more effort, and they will have to we have to change the way we do science, but I think that's the cost we must pay to clean up the social sciences. And if a well-executed super study shows that homeopathy works, I would change my mind. Cool, so that's all from my side. I'm happy to take questions.
Thank you, Jan. That was a really, really interesting talk. And yeah, I guess that reflects a lot of our understanding as skeptics already about the problems with studies, particularly the sort of the p-hacking kind of stuff. So we've got some questions from the chat here. So James Milton asks, given the increasing accessibility of journals to the public, should they be released with annotations that don't assume prior scientific knowledge, for example, explaining correlation versus causation? I must say, James, that I'm impressed that you think that the general public are going to be reading journal articles, but Jan, what's your opinion on this?
So I think there is some amount of kind of, well, it'd be very hard for scientists to write at the same time for a general audience and to their peers. And so we have developed a lingo and some specific terms, and kind of redefining them is going to be a lot of work. But what a lot of journals are doing now, they're asking us to write kind of popular summaries and make press releases and have kind of small like abstracts or significant statements that the general audience should understand. So I think with that, and science journalists hopefully doing a good job of explaining what we're doing, I think that's probably the way forward.
So this is what better science communication is about.
That's what better science, yes. Yeah, that's right.
Yeah, okay. So Luke McGuinness asks, should the names of reviewers of journal papers be published along with the paper? Could this improve the quality / accuracy of papers?
Oh, I don't know. So my instinct is no, because so many scientific fields are fairly small, and you'll see each other's papers go around. And if I've been shown to accept somebody's paper or reject somebody's paper, I might fear being retaliated against. And so I think there's some anonymity allows us to be more critical and more honest. But so there are journals out there. So for example, Frontiers in Psychology, they publish author referee names. So both is happening, but I haven't thought about this very carefully.
Okay, all right. I think we will need to end it there. But thank you very much for your talk. It was great. So thank you, Jan.
Thank you.